Lesson 4.5 Implicitly Defined Functions. Recall, we've done a lot of work with functions this year, and the basic definition of a function is that a function is a relation that maps a set of input values to a set of output values. Given the function y equals f of x, we would say that we're defining x as the input or independent value and y as the output or dependent value. We would also say, based on this format, we would read this as y is a function of x. Y is a function of x. It really doesn't matter what the letters are here. If I were to write x here and y there, x is a function of y, where y is the input and x is the output. The letters are completely arbitrary. It's about the order of information. X is the input, y is the output, y is a function of x. Another way to put this is that there's exactly one value of y for every input value of x from the domain of the function. X represents the domain, y represents the range, x is the input, y is the output. For every input, there's exactly one output. Again, that's in order to define a relation as a function. But not all relations are functions. A relation is any relationship that we have between two variables. With a relation, there may be multiple values of y that satisfy the relationship for each value of x, and vice versa. We don't have a restriction of a particular number of inputs matching a particular number of outputs. That's in order to add the extra qualifier of function. For a relation, any relationship that we have between two variables can be called a relation. Now, to add the qualifier of implicitly and explicitly, that's where we have the idea of rewriting a function in terms of another variable. Y equals a function of x, or y equals a function of t, or x equals a function of r. So if we can get a single variable defined on one side of the equation, then we would say that it is explicitly defined. Here we have an implicitly defined function where, again, all bets are off. It doesn't really matter if it's a single variable by itself. Variables are all mixed together, doesn't really matter. But if I were to simply take this x squared and move it over, I get this statement right here, y equals 2x squared plus 1. This would be called an explicitly defined function, y as a function of x is the input, y is the output, versus this is simply an implicitly defined function. Here we have another x squared plus y squared equals 9. X's and y's are all mixed together. Now, in this case, x squared plus y squared equals 9 technically isn't a function in our definition of a function because x squared plus y squared equals 9 is a circle. It's a circle of radius 3. X squared plus y squared equals r squared. So for any given input, there are two outputs. Now, we could fix this problem by rewriting it as an explicitly defined function. So y equals plus or minus the square root of 9 minus x squared. Technically, it would either be y plus the square root of 9 minus x squared. That would be the top half of the circle. And then y equals negative square root of 9 minus x squared. That would be the bottom half of the circle. So this is technically two different explicitly defined functions. Now, I could just as easily, though, have rewritten it as x equals plus or minus the square root of 9 minus y squared. Subtracting the y squared over and then taking the square root to get rid of the x gives me two separate explicitly defined functions. So it really depends on what is more comfortable for you, what's more useful on what you want to work with. Do you want to work with these types of functions, or are you perfectly fine working with this type of function? In calculus, one of the things we're doing to prepare for calculus is stop restricting yourself to only working with explicitly defined functions. We can work with implicitly defined functions just as well, and we don't restrict ourselves to the arbitrary need to get a variable by itself before we start working on it. Consider this guy right here. We have an implicitly defined function. If I go to try to solve for y, I've got y squared right here, I've got y right here. I'll tell you right now, there is no algebraic way in order to get y by itself in this equation. Likewise, there is no algebraic way to get x by itself in this equation. Just because you've gone through all of your high school career and every single problem has a way to solve it, doesn't mean that's always the case. We purposely give Algebra 1 and Algebra 2 students problems they can solve because they can solve them. If they're not solvable, we're not going to give them to you as a practice problem. Be aware, there's an infinite set of problems out there. The vast majority do not have pretty solutions. So since there's no way to work with this function explicitly, we need to be prepared to work with implicitly defined functions just as easily as we work with explicitly defined functions. The good news is there's really nothing extra you have to do. Just jump into the problem. Whatever the problem is, jump into it. Don't waste your time trying to solve for a variable first. Consider, given 2x squared plus x minus 3 equals y minus 10. Here we have an implicitly defined function because we have all the x's and y's all mixed together. I could start by thinking, okay, how do I rewrite this as y as a function of x or x as a function of y? Or I could just not, because it really doesn't matter. Find the value of x when y equals -1. Okay, so let's figure out what x is when y is -1. Anywhere I see a y, I'm going to replace it with -1, and then I'm going to attempt to solve for x. Let's do it. So rewriting the problem, 2x, but instead of y, I'm going to write -1 squared plus x minus 3 equals -1 minus 10. I now look at what I have remaining. Let's clean up the things that we can clean up. -1 squared, that's just going to be +1. We're left with 2x plus x minus 3 equals, that's just going to be -11 on the right side. So now, this is just an algebra 1 level linear equation. Let's solve for x. We can still have combine these like terms, 3x. I can also move that 3 to the other side. That's going to be -8. X equals -8 thirds. So again, we have an implicitly defined function. I have no idea what the graph of this function looks like, but I now know that it contains the point -8 thirds, comma, -1. I could keep going and find more points, but that's not what today's lesson is about. Let's try this again. Same function. This time I want you to find y when x is -1. Pause here, play when you're ready. Of course, this one was a little bit more challenging because of course it was. Plug in -1 for x. I have 2 -1 y squared plus -1 minus 3 equals y minus 10. So let's clean up what we can clean up. I see this would just be -2y squared. That's going to be -4 equals y minus 10. Okay, so we have a single variable equation, but this time I have y squared and y, so I'm going to treat this as a multivariable equation because I cannot combine y squared and y, which means multivariable. Let's try factoring. If I'm going to factor it, let's move everything to one side. -2y squared minus y, that would be plus 6 equal to 0. Now that it's equal to 0, I can attempt factoring. I have a quadratic trinomial. So I'm going to use the AC method, but I hate when I have a leading negative. So I'm going to go ahead and divide everything by -1 to start with so that I don't have to deal with that leading negative. And now we'll go into our double bubble. 2y going to come down as is. I'm now looking for factors of -12 that add to 1. That would be 4 and 3. +4, -3. Of course, the 2y plus 4 is really y plus 2. And I have 2y minus 3. Factoring is done. Let's go ahead and solve. Y equals -2 and +3/2. So when x equals -1, I have two y values, -2 and +3/2. So I have 2 points on this graph at -1, -2, and -1, 3/2. Now, just for fun, we can go ahead and look at this implicitly defined function in Desmos because Desmos is perfectly capable of graphing implicitly defined functions. Most handheld calculators are not going to be able to handle something like this. So we can see, notice, at x equals -1, I have two output values, one at -2 and the other one at 3/2. Recall that I also asked you to plug in y equals -1. When we plugged in y equals -1, we got an output of -8 thirds, which is right here. Now, the fact that by observation on this graph, it doesn't pass the vertical line test, so I know that this is not y as a function of x. Because it fails the vertical line test, every input value of x has multiple outputs of y. Whether or not I can or can't solve for y in this equation is really irrelevant. On the other hand, it does pass the horizontal line test, so for every input value of y, it does have a single output of x. And by closer inspection of this particular equation, notice if I move the 3 over and then factored out the x out of these two terms and then divided, I could easily rewrite this equation as x equals a function of y. But the fact that I could, again, wasn't relevant for the purposes of this question. An implicitly defined function is nothing to be afraid of. So, where are we going with this? In calculus next year, you're going to learn about a concept called the derivative. The derivative is the instantaneous rate of change of a function. The first half of the year, you're going to spend focusing just on that question. Find the derivative, find the derivative, find the derivative. For different types of functions, there are going to be different rules that you're going to use. Some incredibly easy, some a little bit more challenging. But once you're able to find the derivative, then we also need to do something with the derivative. Often in calculus, the question will start with first step, find the derivative, and then the rest of the problem is a bunch of algebraic and arithmetic manipulation. So in this question, I've gone ahead and given you the derivative. This statement right here represents the derivative of that original function. It's the same function we were working with on part A and part B. So I've gone through and done the calculus for you. Now notice this little statement right here, y prime. That's not y to the first, that's read y prime. Y prime is the notation that we use for the derivative. So the question here is, given this statement, find y prime when y equals -1. That's literally the same question that I did here. Find y when x equals -1. Find x when y equals -1. Here, find y prime when y equals -1. So we're going to treat this guy as the variable that we're solving for. Instead of having two variables in this statement, we now have three variables. Y prime is a separate variable compared to y versus x. So let's do exactly what we did before. We're looking for y prime when y equals -1. Now keep in mind, because we're looking for y prime when y equals -1 and y equals -1 was the same value that we plugged into this equation earlier, we also know that the corresponding x value is -8/3. So we're not just plugging in y equals -1, we're plugging in -8/3. So let's do that. So we're going to say for x is -8/3, y is -1, y prime is unknown, that's what we're solving for, plus 2y, which is -1, squared plus 1 equals y prime, that's our unknown, that's what we're solving for. So just like before, let's clean up the arithmetic first. I see a double negative here, that's going to be a positive. 8/3 times 4, that's just going to be 32/3 times y prime. Plus, that's just going to be 2, actually, that's going to be 3 equals y prime. So now, even though this is technically a calculus question, we're solving for a derivative. This is really an algebra 1 question. We have a single variable equation. We want to get that variable by itself. So I can either subtract y prime from both sides, or I can subtract 32/3 y prime from both sides. I'm going to go ahead and I'm going to subtract the y prime over and then subtract the 3 over. So we'll have -3 over here. And when I subtract y prime, I'm subtracting 3 over 3 y prime. So this 32/3 just became 29/3 y prime. And then getting rid of the 29/3, we're really multiplying by 3 over 29, multiplying by 3 over 29. That gets rid of that fraction, so y prime equals, that would be -9 over 29. Final answer. All right, let's do it again. Here we go. So same original function, same derivative. This time I'm looking for y prime when x equals -1. Recall, we already did x equals -1 into the original function so that we know that there are actually two corresponding y values, y equals -2 and y equals 3/2. Now, because there are two separate y values, that means there are going to be two separate y prime values. We're going to be able to we're going to be able to find the derivative at two separate points. There were 2 points on this curve where x equals -1, so we're looking for two separate answers. So let's do this two separate times. Start by plugging in -2 in for y, just like we're going to plug in x equals -1, we're going to plug in y equals -2, solve for y prime. That's your first answer, and then come back and replace the -2 with 3/2, calculate it again, that's your second answer. Go ahead and pause here, hit play once you've finished with y equals -2, we'll check our answer, and then you can pause it again as you continue to rework it with 3/2, we'll check our answer again. All right, let's take a look. So our derivative is 4x, x is -1, y, we're going to use -2, and then y prime is our unknown, plus 2 times y, which is -2, squared plus 1 equals y prime. So I see a double negative, that's going to be a positive, so that's going to be 8y y prime. That's going to be 4. That's going to be 8 right there, plus 1, which is 9, equals y prime. This one's pretty straightforward. Let's subtract the y prime. We get 7y prime equals negative 9. So y prime equals negative 9 over 7. Final answer. All right, if you haven't done so already, try this again with 3 halves. Trying this again with 3 halves. I'm just going to go ahead and erase the negative 2 and replace it with 3 halves. I guess all of this is going to change, so I can go ahead and get rid of all of that. So 3 halves, 3 halves. So multiplying through, now I notice that the 2 and the 4 are going to cancel out. So I can't see that. So let's use a darker color. So the 2 and the 4, that 4 is going to become a 2. So 2 times 3, that's going to be 6. It's going to be negative 6y prime. And then here, now notice, let's use purple this time. So I've got 2 squared. So one of these 2's is going to cancel, and then this is just going to be 2 to the first. And then that's still going to be 3 to the second. So that would be 9 over 2 plus 1 equals y prime. I'm going to go ahead and move this over here to make it 7y prime. And then I have 9 halves plus 1, which is really 9 halves plus 2 halves, which is 11 halves. Dividing by 7, I get y prime equals 11 over 14. Final answer. All right, one more style of problem that we need to be prepared for. This time, no inputs whatsoever. No x values, no y values. Let's just find y prime. One of the common questions that you're going to have next year is find the derivative at a given point, which is what we just did, but also just find the derivative in terms of x and y. So this is purely an algebra question. I want to get y prime by itself. Here's the equation I'm working with. All right, let me go ahead and just rewrite that equation. 4xy y prime plus 2y squared plus 1 equals y prime. So again, what I'm trying to solve for is the variable. The variable I'm trying to solve for is y prime. Just like we've been doing all throughout Algebra 1 and Algebra 2, let's get the variable on one side of the equation, everything that's not the variable on the other side of the equation. So I am going to make things simple on myself, and I'm going to move this term, just this term, to the right side, because when I do that, minus 4xy prime, I now have an equation where the left side does not contain y prime, the right side does contain y prime. So now that the right side contains all the terms that have y prime, let's go ahead and factor the y prime out. That's going to leave me with 1 minus 4xy. Notice that if I redistribute, I get back to this statement right here. Left side was unmolested. Goal is to get y prime by itself. Y prime is being multiplied by this quantity, so let's divide. So I'm going to rewrite this as y prime equals, it's going to be a big old fraction. This is on the top, 2y squared plus 1. And then this is going to be on the bottom, 1 minus 4xy. Final answer. Now, I will point out that I could have done this problem before doing this problem or this problem, all right? Find y prime when, okay, well, here's y prime always, and then now I could plug in x equals -1 and y equals -2, x equals -1 and y equals 3 halves. I could plug that in right now, and it would spit out the exact same value. It's really a question of what order do you want to do this in? Do you want to plug in the numbers and then solve for the variable? Or do you want to solve for the variable and then plug in the numbers? That's kind of one of those, are you a left Twix guy or a right Twix guy? It really doesn't make a difference. Just pick one. All right, here's a completely new problem. I've given you the original function right here. And then because you don't know calculus yet, I've gone ahead and given you the derivative. All right, here's the original function, the algebraic function. Here is the derivative of that algebraic function. Let's go through the same process that we just did. Let's start with find y when x equals 0. Notice, find y when x equals 0, no mention of the derivative, which means we're going to use this equation right here because this is an equation that contains x and y only. So take a moment, pause here, play when you're ready. Find y when x equals 0, so let's rewrite the equation. y squared, e to the, when we plug in 0 for x, that's going to be e to the 0, 3y plus 0. So e to the 0 is 1, so this just became y squared equals 3y. Pretty straightforward equation, or multivariable equation, because I can't combine this into a single term. So that means we're factoring. If we're factoring, we need to get everything to one side. That's going to be a GCF problem, so we're going to get two answers, y equals 0 and 3. Final answer. Let's do it again. This time find y prime when x equals 0. Because the question says find y prime, that means we have to use this equation. This is the equation that contains y prime. We're going to plug in 0 for x, but when we're plugging in 0 for x, we also need to know that when x equals 0, y equals 0 and y equals 3. So there are two possibilities for y prime. So what you're going to do, just like we did before, plug in x equals 0 and y equals one of its possible values. I'll start with y equals 0. So we can plug in x equals 0 and y equals 0, and then we'll come back, do it again, x equals 0 and y equals 3 to find the two different y primes. Pause here, play when you're ready. All right, starting with x equals 0, y equals 0. So if I'm plugging in y equals 0, plugging a 0 here, that's going to zero out that entire term. No, not even any point to writing it. It's also going to zero out this term. No point to writing it. So that's just going to be 0 on the left side. On the right side, I'm going to have 3y prime. And then I'm also going to zero out that term. So it's just going to be 0. I'm not even going to bother writing it. So y prime equals 0. So when x is 0 and y is 0, y prime is also 0. Let's go through the problem again. This time, when x equals 0, we had another solution where y equals 3. So let's plug in 0 for x, 3 for y, and solve for y prime. This one's going to be a little bit more challenging because we actually have to do something. All right, plugging in 0 for x, that's going to be e to the 0 plus 2 times 3 squared, e to the 0 equals 3y prime, and then 2x, that's just going to be 0. Cleaning it up a little bit, e to the 0 is 1, so this is going to be 6y prime, plus that's going to be 9 times 2, which is 18 times 1, equals 3y prime. I'm going to go ahead and move the 6y prime over to the left, over to the right. That's going to be negative 3y prime. Divide, y prime equals negative 6. So when x equals 0, y prime could equal negative 6, or y prime could equal 0. All right, let's do it one more time. This time, just like before, let's ignore all the input values possible. Let's just solve for y prime. Let's get y prime by itself. Go ahead and try this on your own. Hit play when you're ready. Rewriting the equation. Again, I'm solving for y prime. That's this guy right here and this guy right here. So any term that has a y prime in it, I want to make sure that those terms are on the same side of the equation. Everything else can move to the other side of the equation. So I'm going to move this guy to the left, and I'm going to move this guy to the right. So 2y prime e to the 2x, that'll be minus 3y prime, equals, now this guy is going to become negative 2y squared e to the 2x, and that was a plus 2x, so that is still a plus 2x. That's a 2 right there. All right, just like before, I've got two terms with y prime, so let's factor out the y prime. You'll notice as you're doing a bunch of these problems, it's pretty much the same steps in the same order every single time, which is why we practice. Through repeated practice, we build our muscle memory. We don't even think about what we're doing. We can have entire side conversations while we are solving the problem because we're not even really paying attention to what it is that we're doing. We're just going through the motions because we've done this so many times that we don't even realize, oh, hey, look at that. I've solved the problem. Y prime equals that. Now, of course, there is a lot more to talk about when it comes to implicitly defined functions, and you'll talk all about it next year in calculus. But this is really just the algebra portion. Calculus is just the first step of the problem. You still need to be able to do the algebra to finish up the problem. So you take it from here, pull up the practice, get to work.